Hey, Andrew, I have to ask you, did you just sign in a moment before I did?
Yeah.
That's interesting because what I have noticed is most days when I go to start this class, it asks me if I want to join the class because I guess somebody is already there. And today it said, do you want to start the meeting? So I thought, oh, well, I guess I'm the first one. And yet when I logged in, then immediately you were there. So I guess you must have signed in at really just the same time I did. Well, that's good timing. Oh, I see. I needed to check something here. Where is the syllabus page? I guess let me begin. Guys, we are really at the end of the semester now, so I think we need to just orchestrate how we're going to finish. So this week is half over, right? We had Monday was the 4th, and we're done with that. Today is the 6th. Friday we meet again at this time. I guess I was thinking we could have a review, but people have asked me for discussions of some of the other topics that show up in number theory that have not really been part of the material that we do, and may, in some cases, not even have been mentioned on the syllabus. So if you would like, there are additional topics that we can talk about. I can explain how they fit into the grand scheme of things, but you wouldn't be responsible for them on the final and so on. So really, that's all I had in mind for Friday. For today, I really just wanted to finish the quadratic reciprocity theorem and try out some applications and so on. Then, if this is the end of the regular classes, then that means that next week is when the finals are. And your final is scheduled for Thursday the 14th. Of course, nobody's following the schedule anymore, I guess, but I was thinking that you would have a final exam that would run through the usual period when you would be taking this exam. In other words, if you wanted to take the exam at exactly the time that was scheduled, which was Thursday from 2 to 5 p.m., then you could do it then. But I'm going to assume most of you would prefer the luxury of changing the schedule around a little bit. So then the question for us as a group is, when exactly should we have the starting and ending times be for the final exam? And well, I guess I'm not really supposed to start on Tuesday, am I? These are no class days, is that correct? I think the 11th and 12th, nobody is supposed to have classes and nobody is supposed to have exams. But I could give you the exam as early as the morning of the 13th, and I could have it due as late as, I don't know, sometime at the end of the week. But I don't want you to be stressing over it for a long, long time. So maybe we could have a 2 or maybe 3-day period in there when you would work on the test. Do you guys have a preference for when we should do that? Anybody have any other conflicting exams that they want me in particular to avoid? It's a lot of silence out of everybody. So you're all okay if I just pick a couple of days in there and say this is when you work on it? Well, all right. How about if I just make an executive decision then? How about if I say you can have, here's a 3-day period. I will try to get the exam available to you on the morning of the 13th. And then it has to be due by, I don't know, midnight or something on the 15th. And my thinking here is that the exam would have the same format as the midterm exam. I'll just present a PDF with a bunch of questions on it. Now, this is nominally, you have 3 times as long for the final as you would have for a midterm. What I give you, 5 questions on the midterm exam? I can't imagine you guys want to work through 15 such questions, but there'd be more than 5. I don't know. I'll give you half a dozen or a dozen, somewhere in there, of questions to try. And the topics would be everything that we've done all through the semester. The stuff from the beginning of the semester, I hope at this point you guys are feeling pretty comfortable with, I don't know, the division algorithm and proof by contradiction and some of the early stuff that we did, but I can still give you questions about those topics. But then the more interesting questions are likely to be over this latter half of the semester, which unfortunately more or less coincides with the whole Zoom experience, which I know has been kind of exhausting for everybody. So do you want to make any comments about the final stuff that you want me to put on there or stuff you don't want me to put on there? Something that I should know, because I'm going to have to be preparing the exam this weekend, I guess. I want to make sure I give you some good questions. All right, well, we can discuss this a little more on Friday because I want to review all the topics that I think will be on the test. And you can be thinking in advance of Friday as well. So we'll just, you know, revisit this issue the next time we get together. A couple more things that I should say is before you guys are launching into the exam, I can have office hours. I've already scheduled office hours for my calculus students as well on Monday the 11th from, let's say, 11 to 1. And you guys are welcome to drop in then as well. I don't know if anybody will be visiting me on that day. And then if you want to have meet me at some other time, you know, it's the usual thing. Just send me an email and I'll schedule a Zoom meeting with you. If there's a groundswell of a lot of activity, I suppose that would give me a Tuesday to schedule an office hour as well. While I'm at it, while I'm making calendars, can I just say that any of you that have a mother figure in your life, can you remember that in the US we celebrate Mother's Day on this coming Sunday? So don't spend your whole Sunday studying math unless that makes mom happy, okay? If she's always been bugging you to do your schoolwork, then that's a good reason to do it on Sunday, but otherwise, take a day off. Spend it with your mother. All right, so shall we return to the material that we've been discussing, which is this business of quadratic reciprocity. So I worked out in long detail with you the quadratic character of several small numbers when we're trying to decide whether or not -1 is a prime. That was easy to do. You could express it in terms of whether P is 1 more than a multiple of 4 or 1 less than a multiple of 4, or you could just combine the two into this formula. If you wanted to study the quadratic character of 2, we had a similar formula for that one. And the quadratic character for 3 turned out to be, I forget exactly the formula. It's +1 for the primes that are close to a multiple of 12. And then it's -1 for the primes that are sort of halfway through, more or less halfway through, away from a multiple of 12. Okay, I skipped over an easy one, and the next one is also easy. You guys know this quadratic character, and you know this one. They're both the same, because obviously these numbers are perfect squares in the ring of integers, which means that they're also squares modulo p. So the next example to try would be, well, okay, how about can we decide whether 5 is a prime or not? whether 5 is a square or not modulo p, and exactly the same reasoning that I gave you before for the prime 2, and we worked it out with the prime 3 as well. It continues for any modulus, and it uses Gauss's theorem, where what you do is you just look at the doubling or tripling or quintupling formula and look to see what it does for just the small residues mod p. And well, some of the numbers become large when you double or triple or quintuple them. And when I say large, of course, as integers, they're obviously going to be 5 times as large. But we did observe that when you draw the graph of the function, as it goes from z mod p back to z mod p, then the graph gets too tall and you have to sort of wrap around. This is where getting you guys used to thinking of the integers mod p as being a cyclic group. It cycles, everything cycles around. The whole graph could be written on a cylinder, actually. And so we have to let the multiples of 2 or 3 or 5, we let them wrap around and then see where they end up, and we ask ourselves how many of those small numbers become small or large after you have first multiplied by a and then thrown away the multiples of p. So, well, I'll let you try it. What you discover in this case is it'll depend on the residue of p, where p falls, modulo 20. And the pattern that you see brewing in these first few cases is that if you want to discover whether or not well, let's just say a prime is going to be a square mod p or not, that depends on where p falls modulo 4 times q. So I've worked that out when q is 2 and 3 and 5, and sure enough, we needed to know what p was modulo 8, modulo 12, and this one would be modulo 20. So there's a pattern brewing that says that somehow we should be able to do these calculations without running through a lot of extra steps, potentially having very large primes p, because instead the answer depends only on the smaller prime, the q that we've seen in here. The value of this Legendre symbol depends only on very small multiples. It becomes periodic with a very small period. Well, there is a theorem that guarantees that will always happen. And that's called the Law of Quadratic Reciprocity. And I don't think I've stated it yet. I've mentioned it several times. So let's give this theorem its proper due here. And it says the following: if p and q are both odd primes, then you can in fact decide whether or not q is a square modulo p, and it will just depend on how p sits modulo q. In fact, we're going to work mod q and ask just whether or not p is a prime. Excuse me, whether p is a square modulo q. And the very first step of that process would be to reduce p modulo q, right? If you're looking to see whether something is a square modulo 5, well, you really only need to consider the numbers from 1 through 4, because a number like, I don't know, 29 is congruent to 4 mod 5, and so since 4 is a square, 29 is a square. So based on what you've seen so far, you might expect that this quantity will sort of depend, at the very least it depends on what p reduces to modulo q. In fact, it turns out to matter mostly whether p is a square modulo q or not. So I don't quite need all of the information of what p is modulo q. It's just whether p is a square modulo q. There's a little subtlety because you notice there's some extra factors of 2 showing up in here. And that's because you do kind of need to know where the prime p is modulo 4 as well. It's not just where it is mod q, but where it is modulo 4 times q. And those are the numbers that you're seeing already showing up in the examples we've done. In fact, this is the statement of the theorem of quadratic reciprocity. I'll give you the easiest to understand portion of it first. If P is congruent to 1 modulo 4, or Q is congruent to 1 modulo 4, then in fact, those two Legendre symbols are equal. And since I've already told you that P and Q are supposed to be both odd primes, all the odd primes are congruent to either 1 or to -1 modulo 4. So the only way that this result is not enough to compare this Legendre symbol to that one is in the case where P and Q are both congruent to -1 mod 4. And in that case, I still know the answer, I still know the relationship. In this case, they are negatives of each other. So give me two odd primes at random, 3 times out of 4, the two Legendre symbols are equal. And even in the run remaining time, I know how they're related. They're exactly negatives of each other. So this is a very cool theorem. The usual statement of it, and I think this goes all the way back to Gauss himself, who liked pretty formulas. The usual statement is to say, if you take the two Legendre symbols and you multiply them together, you're either going to have 2 +1s or 2 -1s. Therefore, the product is a +1, except in this case, if one's a +1, then the other's a -1, and you get a -1 as the product. So the general product is always going to be power of -1, and exact, well, of course, because these are both plus or -1. But I know exactly what the product is. It's P -1 over 2 times Q -1 over 2. So as long as one of those two fractions is even, this will be a +1. And here's the case where both of those exponents is an odd, so you get a -1. So this last line doesn't say anything different from the previous one, but it is a lot shorter to write down. And it has some symmetry to it, I guess. Anyway, this is the traditional way to write it. And this is enough for us to be able to determine the quadratic character of really any number modulo any prime. I mean, you might have to do a little bit of work, including some factorization, but it isn't all that hard. So let's just try some reasonable numbers here. Suppose that I take P to be the, suppose I ask you for the quadratic character of the number 1, 2, 3 over, now I'd like to have a fairly big prime over here. So how about if I do the prime that showed up on your last midterm, 10,007. Well, that's hard. I'm going to rely on the fact that I know that this one here at least is prime, so I'll be able to use all of my theorems. Now that numerator 1, 2, 3 is not a prime, so I can't launch into quadratic reciprocity right away. This is obviously equal to 3 times something, 3 times 41 it would be. And now both of those factors are prime. But a fact that we've had a couple of times now using primitive roots was the observation that this Legendre symbol is actually multiplicative. If one of the factors is a square but not the other one, then the product cannot be a square. If each one of them is a square, then clearly their product is a square. But also, if both of them are non-squares, their product magically becomes a square. So I would evaluate this Legendre symbol as the product of these two things. Now, this one we worked out longhand last time. We decided that we could decide the quadratic nature of 3 modulo any prime by just reducing that prime modulo 12. So let's see, 12 into 10,007 is what, 834, I guess, 33. 1/12 is 0.083333. That's how I did that so fast. So if I can just multiply this on the side, sorry, 1668. That's 99. No, that's 10,008. Okay, that's good enough. So 10,008 with a remainder of -1. So this prime right here is congruent to -1 modulo 12. And therefore, according to the calculation we did last time, we know that this quadratic character, this Legendre symbol here, is equal to a +1. Now, this one we did not do last time. We only handled small residues mod p, and I didn't get anywhere close to doing 41. But at this point, I'd like to use the theorem of quadratic reciprocity, because I have one prime over another prime, and I'm trying to decide what the quadratic character is of that one modulo this one. Since at least one of those primes is congruent to 1 mod 4, the 41 is, the 10,007 is not. But as long as one of them is, the quadratic character will be the same in both directions. So this is going to be the same as the quadratic character, the Legendre symbol of 10,007 modulo 41. So if you were expecting big, long computations to follow because that was such a big prime, you can see already that this is going to be much faster. I would begin by simply reducing 10,007 modulo 41. Goes twice, 82, 18, goes 4 times, 164. Remainder is 167, goes another 4 times, 164, remainder is 3. So the number 10,007 is congruent to 3 modulo, that's the Legendre symbol. Let me say that again. 10,007 is congruent to 3 modulo 41. So these two Legendre symbols are equal. And now we're in the same situation of having a 3 as the numerator in our Legendre symbol calculation. So this is something where I can consult the table again. I know that the number 41 is congruent to 5 modulo 12. It's 5 plus 3 12s. So that gives me a -1 for that Legendre symbol. And when I multiply these two together, I therefore know that this number 123 is not a square modulo 10,007. So just a couple of applications of the theorem of quadratic reciprocity. The law of quadratic reciprocity enables me to calculate this pretty fast. The steps that I needed only involved, I did have to be able to factor the smaller number at least, to write it as a product of prime powers. And then for every one of these, well, you saw me consulting my table to make this go quickly, but in fact, I could have done it just using the law of quadratic reciprocity again to turn this into the asking about the quadratic character of a bunch of numbers modulo 3 or 41. Now, in this particular case, you'll notice that when I reduced mod 41, I inverted using quadratic reciprocity, and then I reduced mod 41, and as it turned out, I got a number 3, which I could just consult the table. If I had gotten a number bigger than 3, well, I might have still been able to consult my little table of values, but probably what would have happened, if, for example, this had been a 38, then I would have to start from the beginning again and factor that top piece, and I'd have a 2 over 41 and a 19 over 41, and that would then break into a couple of calculations, which I could use quadratic reciprocity on that one, and for this one I would just end up consulting the table. So every time you go through this process, you will see various Legendre symbols to be computed. You will always have an odd prime down below, at least when you start. By reducing modulo the lower prime, this numerator will always be some number, can be treated as some number between 0 and this lower prime. That's a fairly small integer, or small enough we hope that you can factor it. And therefore this Legendre symbol, just like in this case, you would write that Legendre symbol as a product of several. And every one of those would involve a number that's even smaller than the numerator you already had. So in other words, it would certainly be smaller than the prime that is down below. And all of these numerators would now be primes themselves. And so you could use quadratic reciprocity over and over to keep reducing the pair of numbers, always making the numerator be smaller than the denominator. And after you factor, then you flip it to make the that what was the numerator, excuse me, what was the denominator has become the numerator, and now you make that smaller than the other one. So it's a quick chase that makes all of the individual numbers get small very quickly, and so you can establish the quadratic character. I do need to remind you that the reciprocity only applies to odd primes, so you can't avoid having this extra side calculation. Here you never saw any even numbers show up, but as I said, if this had been a 38, for example, that had shown up, you would have had to say, oh, well, it factors with a 2, and so I would then have to refer to this table. You could have avoided it actually by writing the 38 as being a -3, but there again, you have to write this as -1 times +3, so you'd have odd numbers, but to determine the quadratic character of -1, I would need this part of the table. So if you want to be able to compute the Legendre symbols, quadratic reciprocity becomes your main tool, but at some point, you have to be prepared to just reaching for these two final values. Those will help you get the final numbers. Right? So it's very cool the way it works so quickly. It gets you all the way down to your ±1 without a lot of labor. It doesn't really address the question of what exactly the number is or isn't, well, what the number is the square of when you do get a +1, but that's a separate topic. All right, so what I would like to do is to actually show you a proof of quadratic reciprocity using one of the lemmas we've already got. Now, I worked out the proof of Gauss's lemma for you. I thought, especially for the small values of A, the proof was pretty, I won't say it was obvious or it wasn't even all that easy to follow, but it's easier than some of the other steps, other proofs. They're not really deep, but it does get a little mysterious when they're written out. For example, Eisenstein's lemma, I told you, was a variant of Gauss's lemma. In both cases, you write the Legendre symbol as -1 to a power, and that power had something to do with, well, all these multiples of small numbers. I didn't use this set of symbols in the Gauss's lemma. It is usually used in the statement of Eisenstein's lemma. I'm sorry, you don't see what I'm thinking. This is the floor function, and it's the one that says you calculate this fraction and then round down. And the interpretation of this, whenever you take a number and divide by p, of course you'll get a fraction in general, but the whole number part of it, that's what the floor measures. That is precisely the number of wraparounds. So it's pretty closely related to Gauss's lemma, and it makes it a little bit easier for me to finish the proof of quadratic reciprocity from this. So there's nothing in this that makes it at all clear how two different Legendre symbols could possibly be related, but it looks like a method for calculating just one of them. So here's what I'm going to do now. I want to take you through the proof of quadratic reciprocity that will use Eisenstein's lemma and give you some pretty pictures that clarify why the two quadratic residue symbols could be so closely related. It's almost the same kind of picture that I gave for you last time, where I drew a kind of a graph of all the residues from 0 to p. Well, we only want the invertible ones, splitting here on this non-integer point of p over 2. And last time what I asked you to do was to envision the graph of the doubling function. So you also had the integers from 0 up to p on the vertical edge, and I split things large and small. This time, during the proof of quadratic reciprocity, obviously I have to involve both primes, and so it's a slightly different picture that I'm using. Some of the same principles, but I want to have a picture that takes into account both the prime p and the prime q. And I want to split up all the residues mod q also in half, right along this non-integer line, q over 2. While I'm splitting things up, I'm going to split it up a little bit more. This is splitting the area in half. Now, mind you, it's not It's not quite a diagonal because this isn't quite a square, it's a rectangle. So that's a line with a slope of what, Q over P? All right, so I can give away part of the proof right in here. Although I presented the theorem of quadratic reciprocity for you guys, where'd it go? By breaking it up into these two cases, and I said, yeah, you know, this is just kind of a cutesy way of combining the two cases. In fact, that product right over there will turn out to be relevant. The two Legendre symbols that I'm trying to relate in this theorem are both written as powers of -1. Each one of them will have a very similar formula for the exponent. And so when I multiply the two Legendre symbols together, what I'm going to get will be -1 to the sum of those two numbers. And on the other hand, I'm claiming that the product of the two Legendre symbols is -1 to that exponent. So my job is going to be to show you that this exponent, or more precisely, I just need to know whether it's even or odd, the parity of this exponent is going to be the same as the parity of the sum of the two expressions that I've written out in Eisenstein's lemma. Weird, huh? Well, here's the P minus 1 times Q minus 1 going to show up. It's exactly the number of integer points inside this lower left rectangle. So that's the first observation, is P minus 1 over 2 times Q minus 1 over 2. That's precisely the number of integer points in this rectangle. Okay, so I don't start at 0, of course. I only want the invariable classes, and P over 2 isn't an integer. So that's why I nestled this in just on the inside of that quarter rectangle. And okay, cool. So now what I'm going to do is I'm going to count the numbers that I need to have up here. And actually the way I'm going to do it is to show that the number that you see in the one case is exactly the number of integer points that are below this line. And by symmetry, the number of integer points that are above the line will be the other exponent that I want. So can I sort of shade these in? I'll do it this way and this way. That total number of integer points, it's equal to the number of integer points that are in this part plus the number of integer parts that are in that part. And each one of these things I will show is equal to, well, not actually equal to, but at least congruent mod 2, which is all I care about. It's a good thing these numbers are all just going to be exponents on a -1, so that all I need to know is whether they're even or odd. But this will be congruent to exactly the number that I showed you up in here for, let's see, this one is going to be for P taken modulo Q, and the other one is going to be by symmetry. It'll be the number that's shown in Eisenstein's lemma. Here, let me put it on the screen for you. It's that number that is shown for Q over P. So really that's it. I'm just going to count the number of integer points that are inside here. And this lower, I'll count the lower triangles. I'm going to count these right here. And I'm going to show that that's the same as that weird looking exponent that I wrote there for Eisenstein's lemma. Not really the same. I'm going to throw away some multiples of 2 as I go. But apart from those multiples of 2, the number of integer points in here is going to be that funny expression. Okay, now again, I have to emphasize the same thing I said last time. You think that this is a trivial matter because you know how to compute the area of a triangle. I mean, it's obviously well, I told you the area, the total area is just P minus 1 times P minus 1 over 2, and when you split it with this diagonal, you have two congruent triangles, so each one takes up half the area. But it's the little nuances of just exactly when the integer points are just above or below the line that turns out to be exactly the issue at hand here. It's not about making a really good estimate, but since we need to nail it down to plus or minus 1, you know, an error of 1 messes everything up. So we have to get it precisely. All right, so by symmetry, I have 2 of these jobs to do. I'm just going to focus on the lower one, and the result for the upper one would be the same. So let's just focus on that, on this shaded triangle. Well, there's a bunch of x coordinates. They all go between 0 and p over 2. And they all have y coordinates that are less than they need to be to stay under this line. So I'm going to just say it's, the y coordinate is less than, what would it be, q over p times x. And of course, y is also greater than 0. And we need to figure out how many points there are inside there that have integer coordinates that satisfy both of these inequalities. Okay, well, I got some ideas here. Here's one. I can look at all of those points and look at their x coordinates, and I'll split them into 2 groups depending on the parity of x, whether x is even or odd. So we have those with even x and those with odd x. Now, here's the thing. If you take a number that has an odd x coordinate, if you were to subtract it from p, you would get an even x coordinate because p is odd. If you subtract the y coordinate from q, then what that's going to do is, well, first, when I take the points that are inside, well, take all the points that are in here if you like, subtract all their x coordinates from p, then you'll move them over here. You'll just do a left to right a left to right reflection. If I then follow by subtracting the y coordinates from q, then that would flip things along the horizontal central line and take you up here. So you get a 1-to-1 correspondence. Remember, I just have to count these numbers of these things. And so a 1-to-1 correspondence is good enough. What I'm going to get will be those that have, replacing x with p minus x, I'm going to get those points with even x that's greater than p over 2 and has y that's greater than this inequality, to keep it above the line instead of below the line. Okay, so a 1-to-1 correspondence, actually for any point that's in this lower triangle, subtract the x coordinate from p and the y coordinate from q, and then you'll actually do a 180 rotation around this central point. You'll end up with a point that's over there. And if you start below the line, you end up above the line. And if you start with an even x coordinate, you end up with start with an odd x coordinate, you end up with an even x coordinate. Start with a small x coordinate, you end up with a big x coordinate. Yeah? All right. Now, I can compare the points that are up here that have an even x coordinate and a big y coordinate. I can compare those to the points that are down here that have even x coordinates and the small y coordinate. So I notice I haven't changed this one at all. Just keep that there. So next, what we're looking at is points with even x that's more than p over 2. And let's switch things around to have y coordinates that are less than q over p times x. Now, you wouldn't expect that and this to be the same. So for any given x coordinate, looks like there's a whole lot more y coordinates, a whole lot more integer points down here under the line, under the line than there are over the line. So these two are not actually equal, but I can tell you how they are related. If you took all of the points that have even x coordinates in this range, well, for any x coordinate in this range, if you look at all the points that have a large y coordinate and you add it to the points that have a low y coordinate, you will get all the y coordinates, all the points with any y coordinate. of which there are exactly q minus 1. And that will be true on every one of these vertical lines. So this number that I have in the previous line, it's this quantity, which I haven't changed, plus you get q minus 1 points on every one of those vertical lines, and the number of those vertical lines is exactly whatever it is. It's p minus 1 over 2. So that much counts all of the points that are in this range. Yeah, all of the points that are in this range and have arbitrary y coordinates. So the ones that have, if you want the ones that have a large y coordinate, well, you just throw away the ones that have a small y coordinate. Now, I have to pause here and just point out one thing. I'm using these inequality symbols. These are strict inequality symbols. And so you might be tempted to ask, well, if you throw away the ones that have y coordinates greater than blah, 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 shouldn't this say less than or equal to? But you can't have any points that are actually on this slanted line. You can never have a y coordinate equal to q over p, because p and q are distinct odd primes in the proof of quadratic reciprocity. So no multiple of this is ever going to actually be an integer until this multiplier is at least equal to p, either 0 or less, or p or greater, and that doesn't occur in our figure. So here's where I get away with my mod 2 argument, because mod 2, that's an even number, and so the total number of points shown in the right half of the rectangle is for sure going to be even. There's an even number on every one of these lines, however many lines there are. So mod 2, I don't have to worry about that term at all, and for that matter, I don't really need to worry about the difference between a plus sign and a minus sign. Every calculus student's dream is to live in a land mod 2, so minus signs and plus signs are the same. All right, so what do we got now? If we put these two pieces together, we were looking at all the points that were in this lower rectangle, lower triangle, and they were described by saying that we have, it's the cardinality of all the set of x's that are positive and less than over p over 2. And I also started with y coordinates that are being between 0 and q over p times x. For a while, I ditched that inequality. I changed it to something else, but now I'm again counting only points that have y coordinates less than p over q. So of all of the ones that I listed in the beginning, I separated out the ones that had an even x, and I didn't touch them. Those are the small x's that were even. And then the ones that had an odd x, they have now been replaced with equal cardinality set to points that had a larger x, but the x stayed even. And I turned it so that the y coordinate also satisfied this inequality. So rather than saying that x is between 0 and p over 2, now the right thing to say is that x is somewhere between 0 and p, but it's always even. Okay, so there's the even x's that are less than p over 2, they didn't change, and now we have the even x's that are more than p over 2. They replaced the odd x's that were less than p over 2. All right, so, well, how many such points are there? It's really not hard to count. I mean, the very first x we need to worry about is the number 2. And for that x, we need to take all the y coordinates that are less than 2 times q over p. We want positive integers y that are less than q times 2 divided by p. The number of such y's is this. That's exactly how many y coordinates that you can have when x is equal to 2. Next, you consider what happens if x is equal to 4, and exactly the same argument works. Your upper bound on y is exactly 4 times q over p. Of course, your y is restricted to being an integer, but any positive integer less than that number will work. This is how many such positive integers there are. And so on, the chain continues all the way up to, well, the last x we need to consider will be p minus 1. So it's p minus 1 times q over p. Whatever the integer part is there, that's for x is equal to p minus 1. So what you see me calculating here is a sum of a bunch of greatest integer functions where the greatest integer is always computed of a fraction whose denominator is p, and the numerator is always a multiple of q. The a in Eisenstein's lemma is now a q for us. So it's q times, and here I'm asking you to multiply that by 2x, where x is every small integer up to p over 2. So there they are. There's 2 times 1, 2 times 2, and so on up to 2 times p minus 1 over 2. So this is exactly the number that shows up in Eisenstein's lemma to enable us to compute the quadratic character of q modulo p. And that's just counting points, counting points. We did make one little maneuver that was actually only valid modulo 2. That was right at this stage. So this isn't exactly the number that showed up in Eisenstein's lemma, but it is congruent modulo 2. Did I say? I should have said at this point. That's congruent modulo 2 to the number that shows up in Eisenstein's lemma. And that's the number of integer points in this lower triangle over here. By symmetry, by repeating exactly the same argument, if you count the number of integer points in the other triangle, that will be congruent to, that mod 2, to the number of points, the number in the exponent for Eisenstein's lemma. By the way, it's Eisenstein, not Einstein. Eisenstein's lemma for the other Legendre symbol. And so, as I said at the beginning, when you multiply these two Legendre symbols together, that's minus 1 to an exponent, which is the sum of those two exponents, which is therefore congruent modulo 2 to the total number of points in this rectangle, and that's p minus 1 over 2 times q minus 1 over 2. So it's a pretty and geometric proof, and it puts the two integers p and q in complete symmetry of each other, and it proves, it makes valid all of the calculations that I did at the beginning of the hour when I was actually calculating the quadratic residue symbols. Okay, so comments or questions on this proof of quadratic reciprocity? Okay, I feel like that's an important point to get to in any number theory class. Everybody loves quadratic reciprocity. I have just with 2 minutes left, I don't have a chance to discuss the applications that they show in the book, but I will say that for purposes of primality testing, this is a way of sort of improving on the Fermat test that we have used. The Fermat test says that you know that a number is not prime if you end up computing a to the n and you don't get, sorry, a to the n minus 1, and you don't get a 1 modulo n, then that tells us that n is not prime. It doesn't matter what the a is. And in the same way, if you if you try to use quadratic reciprocity, hoping that a number n is prime, and you discover that the quadratic residue symbol of a mod n is not congruent to minus 1 mod n when a is not a square. I don't need that. When a is not a square, then that also proves that n is not prime. So in a sense, this is an improvement over the Fermat test. I mean, we already know that if n is prime, you should be computing this as a to the n minus 1 over 2. So if you did get a minus 1, then squaring both sides would have given you this one. So it says this quadratic reciprocity technique gives you a way to test for a number to be, for number n to be a prime that goes, in a sense, a step further than what you have over here. When you do discover that a to the n minus 1 is congruent to 1, well then, try cutting that exponent in half and making sure that you get either a +1 or a -1. That should be computed from this power, and on the other hand, you should be able to compute it by quadratic reciprocity if that's prime. So it's a different way to test, an additional test for primality. All right, I'm going to stop here, guys, and I guess this is going to conclude the parts of the course that I'm going to hold you responsible for on the final. What we do on Friday is just going to be like a little introduction to other areas of number theory, and I'll try to tie them in with the topics that we've considered so far this year. Questions? All right, awesome, guys. Come meet me again in office hour. I'll switch to my office hour if you have questions. Otherwise, I will see you on Friday.